Okay, in today's video we're going to go over circuit analysis for a series RLC circuit, and this is a situation that we have. And I just want to point out I previously made a video covering RC circuits and RL circuits, which you can link to in just a moment up here in the upper right hand corner for this video. But in this video we have an RLC circuit, and we're going to go through a circuit analysis for this circuit. And we have a 150 ohm resistor. We have a capacitor that's a 15 microfarad capacitor. We have a 750 millihenry inductor. We have a voltage source, an AC voltage source, 230 volts, and we have that voltage source has a frequency of 55 hertz. Now, in 10 minutes or less, hopefully, we're going to determine the capacitance, the capacitive and the inductive reactance. We're going to draw the impedance phasor diagram, determine the circuit impedance and the phase angle. We're going to determine the current through the circuit. We're going to determine the voltage drop across all the elements, and we are going to draw the voltage phasor diagram and also, once again, to calculate the phase angle. I want to point out, you may notice here in B and in E we have the phase angle. You should get the same phase angle, and you'll see in this video maybe there's a little redundancy. I'll calculate a couple things a couple different ways just to check and see if we get the right answers. Okay, help us confirm. All right, now this is what we have. Here is the information that we were given on the previous slide, and in the first section here we are going to determine the capacitive and the inductive reactance. The reactance for the capacitor and the reactance for the inductor. And that's pretty simple. We're just going to use our basic equations that the capacitive reactance is equal to 1 over 2 pi times the frequency times the capacitance of the capacitor, and we just do that. We plug our values in 2 pi 55 hertz frequency. You'll notice here I put 15 times 10 to the minus 6 because this is a microfarad capacitor. That's 10 to the minus 6, and therefore we get that the capacitive reactance is 193 ohms. Now for the inductor we use the equation 2 times pi times F times L, the frequency times the inductance of the inductor, and therefore it's 2 times pi times 55 hertz, and this inductor is a 750 millihenry, so that's 10 to the minus 3. We multiply those values together and we get 259 ohms. Okay, so that is the capacitive and the inductive reactance. All right, the next thing we said we're going to do is we're going to draw the phasor diagram, determine the impedance and the phase angle. Now here are the values that I'm going to bring over from what we were given that we need to draw the phasor diagram, and I'm going to draw the phasor diagram first. Typically, when we draw the vector representing the resistance, we draw along the positive x-axis like that. When we draw the vector representing the capacitive reactance, we draw along the negative y, and the positive y, we draw the inductive reactance. Now I try to draw these to scale, approximately, but you'll remember that this is the phasor diagram for the impedance. Okay, for our reactances and our resistance, we're going to use this phasor diagram to calculate the impedance. Now remember, the impedance is the sum of all the resistances, or I shouldn't say resistances, all the oppositions to current. Resistors have resistance. The inductor and the capacitor, they have reactance. So it's the sum of all those. Now we have three things. We're going to sum them up vectorially. You'll notice we have two values, two vectors on the y-axis and one on the x. So in order to sum these two up, we're going to take the difference of these two. We're going to add them up, basically. The capacitive reactance being negative, the inductance reactance being positive. So I'm just going to call that x, the sum of these two, xl plus xc. xl is 259. I put a negative because this points in the negative direction, negative 193. So I'm adding a negative value, and I get that the sum of these two vectors is 66 ohms, and it's a positive 66 ohms. Okay, so I'm going to represent that with this, whatever color this is, pink, red vector. That's x, that's the sum of these two. Now I can add this vector to this vector, and then I can get the impedance. And I want to point out that you'll notice this vector points in the positive direction. If the capacitive reactance would have been positive, the capacitive reactance would have been greater than the inductive reactance, then this value would have pointed in the negative direction. So don't get wigged out when you have an example in class where it's positive and then the one you get on your question or your test is negative, and why is it negative, or why is it pointing in the opposite direction. Okay? So it just depends on whether the capacitive or the inductive reactance is greater. In this case, the inductive reactance is greater, so this is going to act more like an inductive circuit. Okay, back to our problem here. We're going to add these two up. I'm going to add those two vectors. Now I can move them because they're vectors as long as I don't change the magnitude or the direction. I can add these head to tail. The sum of those two vectors is the impedance because it's the sum of all the oppositions to current flow or electron flow. And then we have the impedance is Z, this vector. And now we're going to use the Pythagorean theorem because this is a right triangle right here, and we have a squared plus b squared is c squared, and we want to know what c squared is, or we want to know what c is, which in this case is z. And we have our angle phi. That is the angle by which the voltage is going to lead the current in this case because it's a more inductive circuit. So here's our Pythagorean theorem, which I squared both sides, so you took the square root of both sides. So then you get z equals the square root of r squared, this side, plus x squared, which is this side, will give us z. I'm just going to plug the values in. 150 squared, 66 squared, and you get that the impedance of this circuit is 164 ohms. All right, so that is the value that is represented by this vector right here. Now I'm going to do the phase angle, find the phase angle. In this case, because it's a more inductive circuit, it's the angle by which the voltage leads the current in this case. And we have a right triangle once again, so we can use our trig functions. Most of the time this is done with the tangent function, so the arctan of phi is equal to the opposite over the adjacent, opposite x, adjacent r, and then the arctan is equal to x is equal to 66, which we had here, and r is 150, and the arctan of phi in this case, therefore, is 24 degrees. So this angle in here is 24 degrees, and that is the angle by which the voltage is going to lead the current in this circuit. All right, so I think we did those three things. All right, the next thing we want to do is determine the current through the circuit. Now the current, we're going to use Ohm's law, V equals I times R, except because we have an AC circuit here, we're going to have V equals I times Z. R is like the total resistance, but this is the total impedance, which is the reactances and the resistances added together. And therefore we get that I is equal to V, the voltage, divided by Z, and that's the voltage of the source. And that is 230 divided by 164. And therefore we get the current is 1.40 amperes. Now I want to point out that in this video I did not specify whether this voltage is the RMS voltage or whether this voltage is the peak voltage. Pay attention to what you're looking for and what you're given. If in this case this was the RMS voltage, then this would be the RMS current. If this was the peak voltage, then this would be the peak current. And maybe before you start your problem you have to convert between the RMSs and the peaks. Okay, so don't mix up your RMSs and your peaks. Okay, that is the current through the circuit. Now the next thing we're going to do is we're going to get the voltage drops across all three elements: the resistor, the capacitor, and the inductor. And we're just going to use Ohm's law in all three cases. For the resistor, it's V equals I times R. We get 210 volts. We can do the same thing for the capacitor, except we're going to use the capacitive reactance, of course, and we get that V across the capacitor is equal to 272 volts. And we can do the same thing for the inductor, but we use the inductive reactance, and therefore we get that that's 363 volts. All right, now the last thing we're going to do, just as I mentioned earlier, as a confirmation, we can confirm the voltage across the source. In that case, we would use the current. See, the current is the same, but here we use the resistance, here we use the capacitive reactance, here we use the inductive reactance, and here, because it's like the total voltage, and this is the total opposition to current flow, we use the impedance, and we should get that that value is 230. Now, I just do that to confirm. Okay, those two values should be the same. All right, now I want to point out that with Kirchhoff's laws, we know that the sum of the voltage drops should equal the voltage gain. You'll notice if I add these up, it's way over 230. But all of these values are time-varying values because it's an AC source. So they're not going to add these. If these are the peaks, then they're not all going to add up. Or even if they're the RMSs, they're not going to add up. But at any point in time, these three values the voltage drops are going to be equal to the voltage gain, okay, at any particular point in time. You'll notice this one's 363. It's already over. Well, that means that when this is 363, this is going to be some negative value. Okay? Okay. The next thing. Maybe it's the last thing. Okay, we're going to draw the voltage phasor diagram and determine the phase angle. Now, we did previously determine the phase angle, but we're going to do it again and see if we get the same value, which we should, using the voltages. Now, the voltage across the resistor, once again, we draw along the x-axis. The voltage across the capacitor, we draw that vector along the negative y, and for the inductor, we draw that along the positive y-axis. Now, once again, this is the phasor diagram for the voltages. Okay? Now, we want to do a couple things first. We're going to actually check once again, can we get 230 volts out of this? That means we're going to add all of these vectors up, which means we have to add up, first of all, the voltage across the inductor and the voltage across the capacitor to get the sum of those two. I'm going to add all three of these vectors again vectorially, which we already did this once before with the impedances, with the reactances. So I'm just going to do this. We get that if you add this vector and this vector, then you get 91 ohms, and that's represented by this vector. Now I'm going to add them all up again. Remember, this is vector addition, head to tail. The sum of those two vectors is represented by that vector, and that vector should be the source. So now I'm just going to check it, and we have our angle phi again. I'm just going to check it using the Pythagorean theorem. The voltage of the source, a squared plus b squared is c squared. Take the square root of both sides, and you get 210 squared. That's the voltage across the resistor. The 91 is what we got for the sum of the capacitor and the inductor voltages, and we get 230 volts. So once again, I'm just doing this to confirm. I like to confirm, make sure that I got those values, and that tells me that probably these values that I calculated earlier, I calculated correctly. Okay, so we did the phasor diagram, we calculated the voltage, and now we're just going to check once again the phase angle. We should get 24 degrees. We're going to use the tangent function again. You can check it with all three trig functions. The opposite over the adjacent, the voltage across the voltage from the divided by the voltage from the resistor, and we get that is 91 divided by 210, and that means that phi once again is 24 degrees. So that's all we want to do in that video. I tried to go through everything step by step. I tried to do some checks, give me some more confidence that I did those things correctly, and I hope you found that video helpful. If you did, please do all of the following three things. Subscribe to my channel, get all my excellent physics, chemistry, and math videos. Give me a thumbs up for this video, and please leave me a nice positive comment in the comment section. I'm always happy to get your comments and hear what you have to say about the video. So thank you very much. We'll see you in the next video.